What we're going to be talking about is neurology. So before anyone gets nervous, we're going to break it down into two simple components. So all of the nervous system, we're going to break down into two functional components. Okay? I'll explain that, and the functional components are like a construct that we can build everything you need to know about the nervous system on one of two kind of principles. Okay? And it's something as simple as is something that brings you back to neutral or something that brings you away from neutral. Okay? You could look at it that way. Okay? You could also look at it from another perspective of the types of motions that our body does. We have translational motions and we have rotational motions. Okay? In our spine can translate, okay? And it can rotate. Okay? So we're going to go through how that function works. So we need to know the mechanics of our joints, but we also need to know the nervous system and how it controls that whole function. Okay? Another sort of dichotomous, in other words, two-sided perspective on how things work is there's a function of connecting and a function of letting go. Okay? And you could actually take that construct or that sort of metaphor and take it into any aspect of humanity and our functions, our worlds. You could look at it from a psychological perspective. You connect to people, you let go, you know? You connect to an environment, you let go of that environment, right? So everything is about connecting and letting go. So these are some simple metaphors that we're going to kind of build on that allow you to take a tremendous amount of information and make it practical. Okay? If we have a problem, it's probably one of those two things. We have a problem connecting, okay? So what is a connection? A connection is where there's two entities that in some way share some relationship with each other, okay? So if I'm connecting to you, Simo? Yep. If I'm connecting to you, he's staying still, but if I'm moving, he's kind of the axis of rotation, and all of my function is staying connected to him, okay? Or I can turn my head, okay? And my eyes can stay fixed on him, okay? But everything else is moving. You get it? So a connection always has two components that maintain some relationship to each other. And one of the easiest ways of thinking about that is the closest parallel biomechanically is rotation. So in order to have a rotation, you have to have an axis of rotation. Then you have to have some perspective or some point you're measuring from, which is then moving around that point. Everyone get it? Okay? So another function, so that's the ability to connect. Okay? The ability to connect is inherent. Inherent within that is the ability for 2 points to maintain some relationship to each other. Everyone got that? Cool. Very, very simple stuff. If you can't connect, what happens? What happens to your rotation if you don't have an axis of rotation, a clear axis of rotation? The rotation is going to be all over the place. You have instability. Okay? So one of the first problems of connecting, if you can't connect, you'll be unstable. Everyone get that? From a very simple perspective. All right? So the connecting is important. A failure to connect means you can't rotate, you can't remain stable. Right? Because stability lies in the relationship between one thing and another. Perfect. The next component is letting go. Okay, it's important to let go because I could look at Simo all day and not pay attention to anyone else. Okay, just he might feel a little uncomfortable after a while. But if I'm just looking at you all day and I ignore the rest of the crowd, that's fine. You and I can have a great time, right? But I need to let go of Simo. Okay, it wouldn't serve me or him or anyone else to just talk to him and ignore everyone else. So it's important to be able to let go. So if I'm talking about visually, the ability to let go of someone visually we call a saccade. So saccade is I let go of you and I go and I look at Marcus, right? So if I look at Simo, I'm connecting now, then I let go, it's called the saccade, and I connect to someone else. It's called gaze stabilization, okay? So I can stabilize my gaze on Marcus, right? And then I can let go of Marcus, okay? And I can look at Ulla, right? So now I'm going to demonstrate my ability to let go, boom, okay? But now I'm connecting to you. So we have these whole periods of functions where we're cycling back and forth between letting go of things and connecting to things. Everyone understand? It's cool, right? When we let go, when we do a saccade, inherent within that is basically the way we can look at a saccade is like a vector. Okay? I go from here to there. Okay? Forget about the mechanics of what's happening in the eyeball. My vision goes from here, this point in space, to that point in space. Right? How do I do it? I go in a straight line. My eyes don't go like this. It happens quite fast, right? But my eyes don't go on Ula, right? They go from here, boom, there. Very, very fast and efficient. It's a straight line. What's happening to my eyeballs when I go from Marcus to Ula? Are they going at one speed? Are they going and stopping? No. They accelerate, zoom. It's like I fire off muscles that accelerate that muscle. Hit it hard. Wham! These muscles contract super fast and try to accelerate my eyeball. Okay? So between here and Ula, if you broke down the eye motion, if you're able to watch it, we have tools and mechanisms to do that. If you watch the eyeballs between Marcus and Ula, by the time we're about at Hannah, yeah. What's your last? Hannah Marie. By the time I'm at Hannah Marie, it's a total blur, right? It's like my eyeballs are going maximum velocity. After that, my brain is going to start putting the brakes on that movement of my eyeball and slow my eyeball down. Okay? It looks like it's just one fast thing. Well, what's actually happening is it's accelerating to Hannah Marie, and then I'm going to slow my eyeballs down so that I stop on Ula. Okay? So we've hit some of the components of how translations work. Translations work through acceleration and deceleration in a straight line vector. Everyone got it? It's cool, right? These are the two main mechanisms you need to know for everything about the nervous system. Okay? Everything comes down to translations and rotations. That's cool. So we're 5 minutes in. Should we start adjusting now? Great. These are the key components. Okay? So what we're going to do is I want to give you a little bit of an overview of what we're going to do this weekend. I want this to be as practical as possible. The goal here is for everyone on Monday morning to go into clinic with new tools, ready to start practicing these tools. Okay? It's a very different way of doing things, but it's not hard. The hardest thing is what's happening in your head. The way you've always done things is what's going to make it hard. Okay? So students usually find this easier. But we're going to be doing something very, very different. So what we're going to do is we're going to explain a little bit about the nervous system first. So our nervous system relies on information from our sensors to inform our brain of where we are and which way we're moving. Okay? Does that share any parallels to anything I've just said? Where are we and which way are we moving? Where are we? What am I connected to right now? Right? Which way am I moving? Okay? What have I let go of and what direction am I going in? Okay? Where am I and which way am I moving? Okay? Fortunately, we have two different receptor types that give us those two discrete types of information. Okay? Tonic receptors and phasic receptors. So everyone remembers reading about tonic and phasic receptors, right? It was like a little line in the textbook, and then no one ever mentioned it ever again, right? It happens to be one of the most important things in our understanding of neurology and what we're applying, the principles we're applying in adjusted and neutral. Tonic and phasic receptors are massively, massively important. Did everyone get the notes? Everyone has the notes? Okay, great. So even if you didn't read the notes, try to, this evening, when you get home, as tired as you might be, try to read through the notes, even if you're just skimming through the notes, because you're going to hear all the stuff we talked about today, and also the things we're going to hit tomorrow will just be that kind of, be in your mind, and you'll be a little bit more receptive of what we're talking about, okay? So I'm going to go through slides, but I'm going to monologue for a while. So just, if you're waiting for the next slide, just chill, okay? Everything's in the slides are more like notes, okay? I prefer to monologue and just kind of give you guys what you need right now, okay? But we can go through these, and probably we'll spend more time tomorrow morning, but then after lunch, Dr. Schmo is going to give you a depth look on the nervous system as well, okay? So for the moment, I'm just going to talk to you. The nervous system is getting information from proprioceptors that give us tonic and phasic inputs. So what do we mean by that? It's telling us where we are and which way we're moving, okay? If we look at the structure of our nervous system, if we look at all the pathways, the deepest pathways, the ones that are in the most midline of the spinal cord, and the ones that are the most midline of our brainstem and even in our brain, the deepest areas are the oldest areas. They're the oldest areas of our brain. So they share componentry with things that have existed for millions of years. You can go back to fish. Even jellyfish have some of the neurologic components that drive our brain. So what's interesting is when we look back phylogenetically, it means just kind of looking at genetic evolution. When you trace that line back, you get back to things that had very, very primitive nervous systems. And what is it that made this electrical system work? Like, what put electricity in there? Like, what first triggered that whole capacity to have electricity that's sensing the world and activating things? No one knows, right? So it's like, no, we do know. But what it is it's receptors that sense gravity, okay? So gravity is something that's always there. So if once a nervous system was able to perceive gravity, we suddenly had a sensor that could turn gravity, or the effect of gravity, into electricity. So once gravity is creating electricity, if gravity is always there, we're always generating electricity. Okay? Electricity is literally like a charger that's charging up this nervous system of whatever creature we're looking at, and it's constantly giving that system functional capacities. Actually, this reminds me, turn your phone off. Do you have Heidi on? Okay, cool. What we can do is, one second. So, if we trace things back, we go about 400 million years ago, there was jellyfish, and jellyfish had one of the first sensors that sensed gravity, okay? It's called a statocyte. And a statocyte is functionally equivalent to our otolith in our inner ear, okay? It works exactly the same way. You have like a little ball of calcium, which has a mass to it, and it's receptive to inertias, okay? So when the jellyfish tilts one way, this little calcium ball, gravity is going to pull it in one direction, and there's little hair cells that are sensing that, okay? And little hair cells, when they sense it, they get bent. It's going to open up these channels that allow ions to flow across a membrane, and that ionic change within this membrane creates a polarity change, which is actually creating what we need to propagate an electrical signal we call neurological impulse, right? So literally you have like a little stone ball inside a little cell that when it tilts, it generates electricity. How cool. We have the same thing in us. So the otolith in us is in our inner ear is one of the oldest mechanisms that creates electricity for our brain. But what's interesting about that is, for one, it's always creating electricity, okay? Unless you're out in space, okay? Then you have to do other things. That's why the astronauts have to exercise so much, because without gravity, their brain isn't being driven. So one thing is you're always creating electricity, but another thing is you always have an awareness of where you are in relation to gravity. And because these sensors are so old, they're very, very midline, and it means that every evolutionary step that came after that needed electricity. So what is it going to plug into? Well, there's a big cord right over there. Let's just plug it into that. So literally, our otolith and these tonic sensors are literally always, our brain knows it's always going to get electricity from this system. So everything's plugged into it. So as we had evolution opening up and creating and unfolding newer and newer parts of our brain, it's every part of that brain is getting a little bit of a trickle charge from this tonic system. Everyone understand that? Because we also have the phasic system, which is sensing motion, but sometimes we're not moving. What happens if you don't move? If all those brain receptors were tied into our phasic system and relied on us to move all the time to keep our brain alive, okay? If we didn't move, we don't have activation of the cells in our brain. What happens when you don't activate brain cells? They become unhealthy and they die fairly quickly, okay? they need to have a constant activation to be able to, even if there's a little bit of a trickle charge, there has to be some activity. Even if it's an inhibitory signal, it's still creating metabolic function to keep those brain cells alive. If we don't have that, it'll die. So it doesn't make sense for our brain to be connected to movement to keep the brain cells alive. I mean, it does activate your brain, absolutely, and it does keep your brain alive, movement, but it can't be the only mechanism. So the main mechanism that activates and gives the potential for function for our brain are these tonic receptors. So the otolith is one of the most important ones. Okay? You go, okay, no problem. Otolith generally works pretty well, right? It's a pretty reliable source. But we also have other receptors, other tonic receptors. What other types of tonic receptors do we have in the rest of our body? Well, if we think about the midline first, where are we? The spine, right? We're the experts in the spine. What tonic receptors do we have around the spine? Anyone know? We have muscles and we have joints, okay? So in the joints, we have a joint capsule, and the joint capsule has tonic and phasic receptors. So it's generally agreed that the tonic receptors in the joint capsules are called Ruffini endings, okay? So Ruffini endings are a sensor type, a tonic receptor, that in the joint capsule is firing tonically. It means it's always giving information, so no matter what the load is or the pressure on our joint, those Ruffini endings over here are going to be firing off receptors saying, oh, gravity's coming from over here because it's being compressed on this side. That's where gravity is. Okay? So what does it do? Well, it lights up a part of our brain associated with that joint, and that part of the brain becomes active, and it goes, ah, gravity's over here, right? Well, there's also a whole series of joints in our spine. So every one of those joints is going to have a perception of where it is. And what we really want is we want all of those receptors all agreeing about where the load of gravity is. Now, our joint can be in different positions, but gravity should be pulling on every joint in the same direction. Okay? So no matter how you're bending your spine, you're still going to sense that gravity is pulling in that same direction. Everyone understand that? So we have lots and lots of receptors now, not just the otolith. There's many, many receptors from every spinal joint feeding information into our brain saying where gravity is. Okay? Now, as long as all that information is congruent, meaning it's all in agreement, then we know where we are. Right? We know where we are in relation to what? What is the thing we're connecting to? Gravity. Okay? Wherever you look up or look down. Okay? Gravity is where how we know where we are. That's that first connection. That first connection we have through the tonic system is gravity. Okay? So if all the joints are functioning well, no problem. Has anyone ever seen a patient, it's a little bit of a joke, where the joints are not? One joint's in a different direction all the time, every day, everyone, right? Everyone has some joint that's in a different position. So what is that joint? Say we're talking about C3, C4 is bent kind of left anterior. C3, 4, left anterior. What's that joint saying? Where's gravity? To that joint, gravity is coming from somewhere else. You know, gravity is pulling from over here, right? But then the rest of your joints might be in a normal position, right? What does that do to your brain's sense of where you are? It creates kind of a skew in the system. You're like, well, I don't really know where I am. Okay? And that could present itself as something kind of unconscious or even conscious. You know, you could, that's reaching your conscious level, you'd be like, I really don't know where I am. You know, you have someone who has an accident and afterwards they're like, whoa, I really don't know what's going on, where I am. Because you're getting different information. It's dissonance, okay, or incongruent information. So this joint is saying you're over here, and the other joints are saying, no, you're over here. And you feel disoriented. You could feel dizzy, okay? This is what's happening. We have these patients that have these don't know where you are kind of things, and it's happening because you're getting aberrant information, okay? So if you have aberrant information to your brain, you're going to be getting confusing signals. So your whole body and your capacity to respond to that is also going to change. How do you know how to contract your muscles if you don't know where gravity is and how it's going to act on your body, right? Everything will change, okay? We're going to get into some of the pathways, like vestibulospinal pathway that creates stability. If you don't know where you are, you don't know how to stabilize your spine, some subluxations are going to screw up your spinal stability, right? So once we fix these things, we know that in chiropractic, we can take someone's joint and we go, oh, that thing doesn't move, whack, and we can move it, and it's suddenly like, oh, wow, look, I can stand up, I'm nice and stable, I can stand on one leg. We've done something significant to change that person's perception of gravity and where they are, right? It's good stuff, right? That's what we do. We're going to dig into it in a little more depth, okay? Let's just hit the last of the receptors that are kind of our highlights for the weekend, is what is the other tonic receptor in the muscles around the joints in our spine? So we have two different types of receptors in the muscles. We have muscle spindles, okay, and we have Golgi tendon organs, right? So which one is tonic? Take a guess. So muscle spindles tell us about the acceleration of the joint, and the Golgi tendon organs tell us about the load on the joint, right? They're load sensors. So load, gravity. Gravity is a load. So Golgi tendon organs, Ruffini endings, and otolith are our primary proprioceptive tonic receptors. They're always firing, telling us about where the load of gravity is acting on our inner ear, on our joint structures, the load and pressure on our joints, and also the load on the muscles. So load on the muscle would be like the stretch on the muscle. Everyone understand that? Cool stuff, right? Tonic receptors. So just as a quick sideline, without hopefully confusing too much, we also have phasic receptors that are sensing motion. Now motion happens through, we're talking about translational motions, okay? This happens through accelerations. Every time I move my body, that happens via an acceleration. If I go and pick up this glass, I don't pick up the glass with a velocity that looks like a robot. A velocity is like this. It's some movement, a constant movement over time, okay? 100 kilometers per hour, okay? It's a velocity over time. That's not how we move. We move through acceleration and deceleration. If I reach for this glass, what happened? Okay? It's exactly the same scenario as looking from Marco to Ulla. It's like, I'm going from you to you. How do I do it? I accelerate. So my hand accelerates towards the glass, and then I decelerate. I stop there, right? So halfway to the glass, I'm at my maximum velocity, and then I slow down, and I touch the glass, okay? Every motion, our conscious motions, are through accelerations and decelerations. So when we talk about acceleration, I mean accelerate, speeding up, and also mean slowing down, positive, negative acceleration, okay? So we're just going to say acceleration. So every natural motion, every conscious motion that our brain is planning is a type of acceleration, okay? How do I get from this point to this point, okay? From here to here. So if I need to know how to move my body from here to here, I need to know where it is, right? So I need to reference where all that information from the tonic receptors is going. Remember we were saying, if your joint's over here, that's activating a part of your brain that says gravity's over there. Well, those parts of our brain we call somatotopic maps. So we have like a part of our brain associated with every joint, okay, every part of our body. But if the tonic receptors are constantly feeding information into that and telling us where we are and kind of updating these maps, okay? But if a joint is always stuck in one position, what happens to the map? It becomes a little bit skewed. The other parts of the map don't really light up. So say, for instance, my brain is telling the joint to move from this position to this position, okay, but the joint is stuck, it can't move, then when I try to go across that map, my body's going to go, I don't know how to move that joint that way. Or if it's your elbow, you know, your elbow's been injured and it's sort of stuck like this, and then you try to move your elbow afterwards, you're like, or your shoulder or something, you'd be like, it just moves in an awkward, weird way because the maps have been skewed. Everyone understand that? So again, your body relies on the movement of every joint to reach every point in its range of motion to activate and light up all of the map of what the capacity of that joint is, okay? So when the joint hits every position of its function, every part of that map gets activated, okay? If the joint doesn't move, say you have someone with a frozen shoulder, their shoulder's stuck in like this, okay? And they can't light up that map for their arm being in other positions. When they try to move their arm to, and getting close to that and moving past those weird positions, their arm's going to move in a weird way because they just don't know where they are. Everyone get it? I'm being very simplistic here. But when the tonic system starts to fail, okay, probably because the joints aren't moving, then the maps become skewed. We don't know where you are. And in order to be able to plan how to move from one place to the next, your brain plans it because it says, okay, we're in this part of the map.